The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Joe Ferzli, he's a principal at Cary, Kopczynski and Company in Bellevue. He's going to talk about seismic design in the new age of PBD.
Hello everyone, thank you for attending. The presentation that I'm going to go about today is basically a collection of observations on, and it's basically related to core wall buildings in urban environments. So over the past decade, as the previous speakers said, there's been an explosion in a high-rise building and on the west coast of the United States. A lot of it had to go high, and they had to find innovative ways to make these buildings market efficient. And you can see here a collection of a number of performance-based buildings that my company has been involved in the past decade. And we're going to be talking about how we went about different core wall configuration, some of the forces, dynamic amplification, and other topics, and the innovative way to do coupling beams in these core walls. So this is basically, and this has been presented previously, but this is a code prescriptive. The code is prescriptive and restrictive to the design. And I believe PBD explosion happened due to the, it was basically market driven. A lot of urban sprawl happened in the past decade, and a lot of these buildings became high-rise residential buildings, not office buildings. The floor-to-floor height was limited. You want open space and balconies and so on. And the codes did not provide an avenue for, a prescriptive code did not provide an avenue for structural engineers to create that, so they met the market demand by creating, by going about using performance-based seismic design and proving that these buildings would work, which was great. But then we added to it the layers of restrictions, which is good because it created guidelines right now. But these guidelines are also moving, but helped a lot because a decade ago, not having those guidelines was kind of no man. It's kind of open. It's like the wild, wild west when it came to performance-based design on some of these things. Every peer reviewer had opinions different than the others. So when you were working between different peer reviewers, you had to basically translate and work with their basically what they prefer and so on and so forth, and maybe argue about the fact what you think is better. So moving on to talk about core walls and specifically shear walls and how you would look at the core walls. So this is basically a diagrammatical and a lot of basics. I want to go back to the basics of shear walls here. So this is a building, let's say the red is your shear wall. And when you have a building, a cantilevered element, usually your most susceptible hinge is at the base or a podium. And then when you create a coupled wall, what you basically create in a coupled wall is a number of elements that could hinge and dissipate energy throughout the building. That's why a coupled wall is a very important topic for all of us. Actually, 318H has been passing a ballot about coupled wall systems, and then there's also an initiative to do a P695 study. Research been funded to basically quantify what's the R value for coupled wall systems, because the code currently does not really differentiate between regular shear walls and coupled walls. This is how the great thing about coupled wall is if you have two single, you basically increase the moment arm of your system, and then it creates more basically girth to your lateral walls, lateral resisting system. And then you go from basically one energy dissipation element or a couple of them along. If this is your high-rise building, it's either if it's a 400-foot tower or 500. Then you end up with coupled walls. You punch a bunch of opening in the building, you detail it properly, and you get all this coupling beam that creates a lot of energy dissipation that is very valuable for your design, and we'll talk about that a little bit down the road. So core walls, not all core walls are the same. Even though they all look the same, they're not very much the same, because the opening in the core wall very much it varies the behavior of the core wall from the torsional aspect, from the shear demand and moment demand and drifts for that matter. So this is a collection of core walls, and what I show here, I picked up a few of them that we have dealt with in the past. And you can see here the spandrel depth. A lot of these core walls I'll be talking about, they're basically buildings between 400 and 500 foot towers. And a lot of those are done on the West Coast, all of them basically. And the spandrel depth, the slenderness of these cores, as the previous speaker mentioned, is becoming slender and slender. These core walls vary in slenderness between a height to depth ratio of 10 to 14 for that matter. And you could see from right here, this core wall basically we're going to talk a bit about this, how the behavior changes if you have coupling beam in one direction and none in the other. And you have an extremely symmetric core, as this one was coupling beam in all directions, and a combination of other core walls systems. So as designers, we basically, we designed this seismic performance base space. So you have your DBE is right in the middle. You've seen that checker system before, and basically this is the MCE level. DBE is about plus or minus 2/3 the MCE, and then your service level earthquake. A lot of jurisdictions, there's along the West Coast, allows you to do either service level and MCE, or you have to do DBE, MCE, and service level for that matter. So going on to the first case study, this is basically a tower that is 42 stories and 5 levels below grade. It pushed a stamp tower in an urban infill site. It's a residential building. It's about 11,000 square foot floor plate. This is a core coming up. You can see it here. And you have basically a span to depth ratio on that core about 12. And then you have coupling beams, 2 coupling beams in the X direction and no coupling beams in the Y direction. This is basically the core goes around the elevators and stairs. And it's concentric to the floor plate. The floors are basically 7.5 inch PT slabs. The whole thing is basically concrete. So, taking on this specific building, we used 7 pairs of ground motion. And looking at I want to focus on looking at the shear. So this plot shows the shear distribution along the height of the building is basically the envelope shear due to the mean of 7 pairs of ground motion plus a sigma. And then right here is the shear values. And you could see clearly here that the red is basically the shear value of that core, the shear in the Y direction where you have the coupling beam. And the maximum shear in that direction is coming at about 4,500 plus or minus. For the same core, we have a solid wall. There is a major amplification of the shear and without any basically coupling beam, all the way to about at the same level of the 4,500 to about 12,000 kips. And that tells you, this is basically a great example of how the core configuration is so crucial to how you lay out your building, and you should be involved with the geometry of the core from day one. And I don't think there's any architects here in this audience, so make sure you drive the core openings and try to work with the architect for that matter. But creating that symmetry in the core is very important in putting openings in it. So looking at the spectral response forces, they're a bit deceiving versus what we just saw earlier, even though it's not normalized to the MCE level forces, but just looking at the response spectra from the code in the Y direction, basically the force about 2,500, and whereas the perform here. So looking at the Y direction, we have the coupling beam. This is the spectral response response shear, and it's about 2,500. And the performance-based design shear mean plus sigma right here is the 4,500 we saw earlier. So the amplification is about twice on that when you have the coupled beam. The uncoupled beam side is much more than that. So going to another case study of a tapered core, and looking at this core basically is for an office building. It goes up about 500 feet, and we basically truncated the core up 2/3 up the building because of the dropping of the elevator banks. And you could see here in one direction you have coupling beams, in the other direction you have limited coupling beams. So we studied the core in two ways. One way you could see here the diagram, the core have coupling beam on all three walls, and let's say this is the vertical axis is the y direction and the horizontal axis the x direction. And then looking at it as using only one coupling beam as would the architectural layout wanted to have. And the core shear, and this is the shears on this graph right here is basically also the mean of 7 pairs of ground motions applied on a nonlinear perform model. The height of the building is about 450. It's an office building. It's about 31 stories. And you could see here when you have the three coupling beam, the shear, the maximum shear is about level 1 or 2, and it's about 11,000 kips or 12,500 kips. Whereas when you eliminate those two additional coupling beam on the lower portion of the core, that shear goes up all the way to about 20,000+. So what is dynamic amplification? It's actually, there's a lot of literature on that. A great reference would be the design of the seismic design of reinforced concrete building by Jack Maley. And basically, there's a couple of things. If you think about it, you want to take it down to, like, there's two factors that really affect your dynamic amplifications. This one is material overstrength, reinforcing overstrength, and the other one is your higher mode effect. So looking at higher mode effect in particular, and you could see here, if this is your shear wall, or core wall, specifically a shear wall, and then this is a shear at the base, and at your first mode, the distribution of the forces is more or less like you see here. So you have an edge effect is about 2/3 the height of the building. And then the moment at the base, since you're going to start having some hinging, is, let's say, the MPR right here is driven by that lateral force. So the VB and the MPR are affected by that force and the effective height. When you start, the inertial forces changes with different modes, and they vary along the way, and the centroid of these forces would be dropping to a lower arm. By creating a lower arm, the VB right here, that the denominator you reduce that, then the force, the shear goes up. The moment are not as much affected with it. However, the shear on these cores are very dramatic, and we've experienced this in a whole lot of core wall designs. So take, for instance, this core right here. And if we plot the shear due to the level of service and DBE and basically MCE level, maximum considered earthquake level, and you can see here the variation along the y-axis, the height of the building, and this is about 500 feet. And you can see that the shear in the core, this is the overall shear in the core, is basically at the MCE level is the highest. When you get to the blue line right here at the base, this is basically the dynamic base. That reversal here is because you have about 5 levels below grade, and then this is basically the dynamic base where you have basement wall tying in that slab diaphragm into the base of the building. When you come to the wind, and these are wind tunnel results, is the shear is almost insignificant. However, you have to be concerned about drift when it comes to wind. You have more stringent drift than we have in seismic. And then the level of service level earthquake is also at a lower level. But there is a big delta between the DBE level and basically the MCE level shear at the base of that core. And it varies along the way. When it comes to moment, for the same core, the moment at the base is not as dramatic variation in it as far as magnitude as would be the shear. However, on the upper levels, you will see that the MCE level have, you'll experience higher moments on the upper levels due to higher mode effect, and that are if you use just the design, the DBE level design and the spectral response design, you'll be under-designing these upper levels for moments. So, having said all of this, talked about the coupling beam, let's talk a little bit more about the coupling beam. And what we're able to do these days was using the performance-based analysis and come up with innovative ways to do these coupling beams. Since this is basically your energy dissipation element that you're counting on in a core configuration to dissipate in a ductile way the energy of the earthquakes. So this is your diagonal coupling beam, and this is a traditional one. And you have basically, and this is actually not a very heavy one. A lot of these bars usually are number 14 and 11s. And what it does is basically it clashes through boundary elements. It goes up through the floor, and it basically when you put the wall below it, these bars you cannot literally move them around because they're already cast in the floor below. So bringing another boundary element on top of it is hard to get in. And a lot of times they become non-code compliant as far as confinement around this diagonal reinforcement, because it's almost impossible to get this angle in and get these horizontal ties in place accurately so that it would meet the confining equations of the code. So what we have been looking at, and my company has been looking at this for many years, is implementing a fiber link beam. We've worked and what you see here on the screen is your conventional diagonal beam, and right here is equivalent capacity diagonal beam model, but the difference between these two is between this is a boundary element, that's another boundary element of the core, that's the opening to the core, or between two walls, and the difference between these two is that that concrete from this face to this face is basically using steel fibers, high-strength steel fibers reinforcement. So basically you're able to drop the reinforcement between 40 to 60% depending on your beam by just doing so. So what are those? This is the first generation of beams we have used, which is now has been improved through more testing and more data. But what we have used is basically the BEKAERT steel fiber. It's about an inch and basically a little less than an inch and a quarter. The strength is 445 KSI. These fiber are highly extruded, so the diameter of them is very small. And the first generation of these beams, we used about a 1.5% volume, which is about 200 pounds of fibers in a yard, which is quite a bit of fibers. You cannot pump it, but you could bucket it. And what we did, these beams have been tested in a number of locations. The University of Michigan started the testing, and then the University of Wisconsin continued on that, and then there was a Pankow fund that was given a couple of years ago that actually tested more coupling beam, span to depth ratio, and a little bit more in-depth analysis on the whole application. And this is a full test panel. These are the two walls. These are the coupling beams, and they had a control coupling beam that had the conventional reinforcement in it. And when I say conventional, it was not diagonal. It was just a special moment frame, because the diagonal beams perform real well on these things, but they were trying to compare the constructability of a conventional reinforced beam versus and the behavior versus a special reinforced beam. So this is the outcome of the test. You could see how you have about thousands of these little fibers in that concrete, and therefore you mitigated quite a bit of the cracking in this concrete beam, versus what you'll have was a reinforced beam where even if you put 4 inches on center ties or confinement, you're gonna still have some breakouts of concrete under high rotations. So a lot of testing has been done on these special fiber reinforced concrete beams. You have a span to depth ratio of 1.75, 2.75, and 3.3. And this shows you the crack pattern on the testing at the 3% and a 5% drift. This is a test specimen. These right here mimics the core, the concrete walls. This is the beam tested upside down. It's easier to do that. And then there's basically cyclical loading applied on the upper wall, and these two basically ties in the coupled wall system, so you don't have any slippage, and creates a rotation at the end of the beam that are not quite rotation but are due to bond slippage. So they basically have a better results out of it that basically just test the beam itself instead of counting on bond slippage of the bars. So you can see here, the cracking is spread out through the entire beam, and you don't have any major cracks through the beam. And this is at a 5% drift. So as designer now, this is basically the space you design coupling beam in, and also there's a steel beam that has a difference here. But as far as concrete beams, you have the horizontal beam, special moment frame beams right here that by code, according to the HPFRC 318, you can design those, are effective with the span to depth ratio. This is the x-axis is span to depth ratio of the beam, and the y-axis basically shear values in the function of the root of FC prime. And you can see here that above 4, most of the time you will be using special moment frame beam because the span to depth ratio expands, and then therefore a diagonal beam does not work very well because the angle of it drops dramatically. The zone between 2 and 4, you could still use a special moment frame beam. However, it becomes really unconstructable because of all the rebar requirement in it. But the diagonal beam become your number one choice, and you can go up to 8.5 root of F prime C. Below 2, you basically want to stick to diagonally reinforced beams and use strut and tie method for deep beams below that. Now that area right here in the middle between 1.75 and 3.3 is basically the new space of special fiber reinforced concrete beam that we have been using on a number of cores, and that kind of give you another tool in your toolbox to use in case other diagonal or a special moment frame beam does not work for you for your forces in the core. So the biggest application of this was on a project called Lincoln Square Expansion in Bellevue. This project is basically it's urban infill by excellence. You have an office building, which is a 31-story. You have a hotel. This is W Hotel. This has been completed. This is the recent shot of the building. And you have a residence on top. The two buildings are 450-foot tower. And you have a podium of retail and amenities. And then below grade, you have 6 levels of below grade structure. The entire job is about close to 2.7 million square feet. On this this is a steel floors, and all this building right here is concrete floors. The two buildings have concrete cores. So this slide kind of shows what we did is we used performance 3D perform to analyze the building as a nonlinear using nonlinear analysis. We had 11 pairs of ground motion applied, and you can see here basically the behavior of the cores at a different. Obviously, this movement is exaggerated. That's the base right here, and we actually modeled everything at lengths. We have about 5,822 nodes into this perform model. It takes a few days to run, but what we did also in this model as well is basically we had about 396 coupling beam, which 341 of them were fiber link beams that were implemented in the two cores. And you could see here actually on the North Tower you have a core wall, and also as well as a blade wall all the way throughout to kind of mitigate some of that eccentricity, because we're pushed to have the core on one side. It's a hotel, it's hard to get it in the middle, but for a long floor plate as such. So how did we do that? Basically, for that particular job, we took a couple of hysteresis loop from the testing done on fiber link beam that were actually with a span to depth ratio that bounded the span to depth ratios we have on that project for the two different towers. And the span to depth ratio of the coupling beam varied between 2.5 to 3.3. And we use this, the blue is basically the tested specimen. The red is basically the nonlinear model of the backbone curve that was used to degrade and analyze this coupling beam in the nonlinear model that we have showed you earlier. And then we took, we checked, we did the design criteria, we checked the rotation of these beams and made sure everything is working, and then we took the forces and we designed the beam more or less like a special moment frame beam, and we attributed for that case, even though the testing say you can use more than up to 5% root of FC prime as shear in the concrete. So now the concrete is being used for something besides just holding the rebar together, like you design either a diagonal beam or basically a special moment frame beam, because you use VC equal to 0. Here, your VC now is attributing to the shear capacity of the beam and then is there to do its job, and therefore you're able, and then the remainder of that shear is used basically, is been resisted by the shear steel, and you use the MPR and VPR approach. And what you do in the middle, since you have so many fibers, you can drop the confinement. So the confinement in the testing was done at the ends of the coupling beams, and then the rest of the coupling beam had just shear steel, because the fibers by himself creates confinement in the beam. And then what it does to you, this is basically an example of how the beam would look like. You can see the horizontal bar is light, you have confinement at the ends and then shear steel in the middle, and you're able to basically put penetration in location where your shear section would work. But basically a lot of these coupling beams, after a certain level, penetrations are acceptable because you don't have the confinement that restricts you from the penetration into the core and outside the core. That works well with building functionality. So we have done about 4 towers like this. And you know, these are the coupling beams that are here. This is a close-up look to them, and you can see that actually a lot of question comes up is, what about the concrete? How it's going to look like with all these fibers in it? It doesn't look very different than what the regular concrete. This concrete right here is fiber concrete. This concrete is regular concrete. And because of the fibers are so small, the paste kind of covered them. The only time you may see some variation between the two is at the joint interface if there is some remnants of fibers. Beside that, it's the same fiber. And then looking at that, you know, the compressive strength was a little bit higher than you would expect because of all the fibers. So you have to, there's a testing procedure to be, you know, obviously you have adding fiber in your mix, and the best way to add these fibers is in the batch plan. So you take all that, all these problems in installing reinforcement in the field, and then take it to the batch plan, put fibers there, let them mix it, bring it to the batch plan. The concrete ready mixer don't like it very much, but sure does help a lot to save quite a bit of time on the field, especially when you have a lot of coupling beams in the core. So that concludes my presentation. Thank you very much.
We have time for questions.
Yes?
For the shear friction check, I know you had the joint right up against the wall, but let's say you could get it 6 inches in or something like that. Is there a shear friction benefit that's demonstrated?
So what we did is, well, you know, it's also constructability effect. You know, there's a little bit of benefit if you get the fibers into the wall, then they'll can participate at that in the moment. You know, we don't use fibers because we stop them at the wall. We don't use these fibers as a moment. That's 15% of the moment could be, you know, resisted by the fibers. So if you take it further into the boundary element, yes, how are you going to do that? It's pretty darn hard unless you put the whole thing in fibers. Now what we did, we basically shifted, we add some U-bars for the testing to shift that hinge further into the beam instead of into the boundary. Yes?
Any durability or corrosion concern of the steel fiber when you put the coupling beams in steel?
Well, you know, I got that question too, but you know, we never tested it underwater and under environment. But you know, these, you know, I don't, you know, a lot of times, a lot of these cores, because of the energy code, you know, they're covered. It's very seldom you see them exposed to the weather conditions above grade, maybe below grade, but you don't have much weather going on below grade anyway. So I don't know how that would affect the rustiness of these fibers. But these fibers are highly extruded material, so they're very resilient.
All right, thank you.